In this set of notes, we're going to look at some regression pitfalls that you want to be aware of. Regression analysis is a powerful tool for modeling a response variable and can be modeled with ease using statistical software. However, it's often one of the most abused statistical procedures when used by an unwary analyst. So again, I really want to caution you that when you're using regression, it's a great tool, very powerful, but we want to make sure that we use it correctly. So one of the things we need to consider when applying regression is whether or not our data is observational or does it come from a designed experiment. So it's a powerful tool for observational data and designed experiments. It can be used with either type. However, the conclusions we draw depend on how we obtained our data. If the data are obtained from an observational study, then we can only say that the independent variable contributes information for the prediction of y and nothing more. However, if the data were the results of a well-designed experiment, then we could start talking about cause and effect relationships. So where your data comes from is extremely important, especially when you consider a lot of times we're going to be using secondary data. Secondary data is most likely not from a designed experiment, so we want to be very careful how we talk about our results. And so just to remember, it's dangerous to deduce cause and effect relationships with observational data. And only with properly designed experiments can we establish that cause and effect. And that is a bit of an oversimplification. There's a causal inference course that you could take, but that's a good general rule of thumb. And so here's kind of a diagram that talks about what we can and what we cannot do. And there's two big ideas that we always have to consider, and you probably talked about these in your introductory statistics course. They're the idea of random assignment, in other words, how is the treatment assigned to the observations, and then how are the observations selected from the population. So when we select things from the population or select a sample, we could either select it randomly or not randomly, and then if we think of assigning a treatment, that treatment can either be assigned randomly or not randomly. And so depending on which of these were performed, that usually determines the type of inference we're able to make. So for example, if we randomly select our sample and we have random assignment of the treatments, then we can generalize our results to the population and we can say something about cause and effect. And this is what we would call an ideal experiment. On the other hand, if we have random assignment, but our sample was not randomly selected from the population, we can still say something about cause and effect, but we can't generalize it to the entire population. And this is actually where a majority of experiments fall. If we have random sampling, but no random assignment, and we can't say anything about cause and effect, but we can't generalize to the population, and this is where most observational studies fall. And then if we don't have random sampling, we have no random assignment, we really can't say much of anything, and this is just a bad observational study. All right, so let's look at some examples here. We're going to classify each of the following as observation or an experiment, and we're going to identify any weaknesses in each study. So according to a 2007 issue of Bipolar Disorders, 48 adult patients with a diagnosis of schizoaffective disorder, bipolar type, were randomly assigned to two treatment groups. Patients in one group receive topoprimate, and patients in the other group received a placebo. Patients were assigned using the positive and negative syndrome scale, or assessed rather, not assigned. So notice here, since we are doing random assignment, and we can see that here, this is going to be an experiment. Now, if our population we're interested in here are all patients with a diagnosis of schizoaffective disorder, obviously these 48 patients were probably not randomly selected from all patients with that diagnosis. So here we are going to be able to hopefully look at a cause and effect relationship comparing the treatment to the placebo. So in other words, we'll be able to say whether or not the treatment is effective, but generalizing that to the entire population will be difficult because we haven't randomly selected our sample. And this is pretty standard for most experiments are going to be set up this way. And B, a researcher studies the number of mishandled baggage reports per thousands of passengers for January through September 2014 and the percentage of on-time arrivals for the 12 months ending in September 2014 from a U.S. airline. So notice for this one, there is no experiment. We're not randomly assigning any type of treatment, so this would be an observational study. Another pitfall we need to talk about is parameter estimability and interpretation. Insufficient data for levels of either a quantitative or qualitative or categorical independent variable can result in what are called inestimable regression parameters. So let's look at an example here. Suppose we want to fit a model to relate a developmentally challenged child's creativity score Y to the child's flexibility score X. Suppose we fit a first-order model and collect data from 3 students having a flexibility score of 5. So what we're saying here is we're going to fit that first-order model, and if you remember the first-order model, that's basically going to be that simple linear regression model. And we know that this model is a straight line. So if we plotted our data and our data looks something like this, the question would be which line should go through these 3 points. And one thing to keep in mind is we can't have a line that looks like this. In linear regression, you can't have a line that is completely vertical. So keeping that in mind, the question is what line would best fit? Should we do a line that looks like this? Should we do a line that looks like this? One that looks like this? We can't determine, and it's because when we look at the x, we only collected x values at the level 5. In other words, we have no variability along the x-axis. If we don't have any variability in our explanatory or predictor variable, there's no way to estimate this line. And so this is a case where we're not going to be doing anything. And part of the reason that we can't estimate, by using that vertical line is a vertical line, the slope doesn't exist. So that's why that line won't work. So the parameters of the straight line model cannot be estimated when all of the data are in a straight vertical line. We need at least 2 x values, and so this would be a case where the parameters are not estimable. Suppose we wanted to fit a second order model and collect data from 6 students, all having flexibility score 5 or 7. So notice in this case we do have variability in x, but since now we're going to fit a second order model, we have the exact same problem. There's an infinite number of lines that we could fit through these. We're not going to be able to find the one with the best fit. So again, we have another problem where the parameters are not estimable. And in this case, we would need at least 3 different x values. So in general, if we talk about fitting a pth order polynomial regression model, we need that the number of levels of x must be greater than or equal to p plus 1. So this talks about how much variability we need along the x-axis. Further, we also have a requirement on the sample size. The sample size n must be greater than p plus 1 in order to have sufficient degrees of freedom for estimating the variance. So let's look at an example here. So previously we investigated a model for diesel engine performance Y, measured as mass burning rate per degrees of crank angle as a function of 2 qualitative or categorical predictors, fuel type at 3 levels and engine brand at 2 levels. So we've got our 3 different fuel types and we've got our 2 different brands. And so we've seen this example before. So suppose that we got a different set of data than we did previously. So here's our new set of data. And notice that we don't have any data here and we don't have any data here. In other words, we don't have data for fuel type 3 brand 1 or fuel type 1 brand 2. So for this example, we can see that we don't have data for all combinations of fuel type and brand. This is actually going to result with a problem with parameter estimability. So for example, we can look at the SAS output, and so the SAS output for the degrees of freedom of model 3 does not match the number of parameters. So let's first talk about what model we would use here. So suppose that the model that we wanted to fit would be this model right here. And this is the model we looked at previously for this example. And just as a reminder here, remember, since these were categorical, we did have to set up dummy variables for the fuel type and for the brand. So that's why we've got, X1, X2, and X3 as main effects, even though we only have 2 different predictor variables. So I would take a moment, go and look at this example previously and how we set those up. All right, so notice if we go down to the SAS output, we're going to see that not all of the parameters can be estimated. And the reason for that is we don't have data for all of the possible combinations. So let's look at some of these. So notice here, we don't have data for the X1, X3, X2, X3, in other words, those interactions. It's estimating the parameter at 0. So even though these beta estimates are 0, this doesn't mean that there's no interaction. It just means there's not enough information in the sample data to estimate that interaction. And again, it's because for some of these combinations, we don't have any data. If we don't have any data for the combinations, we're not going to be able to estimate that interaction. And we can see here that SAS does give us a warning here to let us know it's not that these variables or these parameters are estimated to be 0, it's that we don't have the data. Another common misconception regarding parameter estimates is that the magnitude of beta hat determines the importance of that predictor variable. This is not the case. We must look at the value of beta hat relative to its standard error. Therefore, some statistical software also reports what are called the standardized regression coefficients. And these standardized regression coefficients make it more feasible to compare parameter estimates since the units are the same. However, you should still be wary of using standardized regression coefficients as the only determinant of independent variables' importance. In other words, we've seen other ways to look at this. We've looked at those nested f-tests, for example. That's a very good way to determine whether or not those betas should be included in the model. And we've seen that in particular when we're looking at higher order terms. We've done nested f-test where our full model includes the higher order terms and the reduced model does not. Another important topic we need to be cognizant of is multicollinearity. When a model to fit includes k predictor variables, there's said to be multicollinearity if there's a strong linear relationship between values of the predictors. Geometrically, this means that the scatter plot values of the predictor variables as points in k-dimensional space fall approximately on a hyperplane or lower dimensional plane. One way to think of this is if you could use one variable to easily predict another predictor variable, then you might have multicollinearity. So, for example, if I looked at my age in years and I also include my age in days, well, I could easily take my age in days to figure out what my age in years are. So if I used both of those as a predictor variable, I'm probably going to have multicollinearity. Severe multicollinearity leads to instability of estimated coefficients and to various other problems. And so we're going to consider the effect that multicollinearity could have on the sample regression coefficients, the estimated standard deviation of the sample regression coefficients, the t-statistics, and the prediction of the response variable. And so there's several signs of multicollinearity that you want to be aware of. And so I'm going to have you pause the video and just read through these different signs. So these are all things that you want to look out for. And it's generally thought that multicollinearity does not adversely affect the ability of the sample regression equation to predict the response variable as long as you restrict inferences to values of the independent variable that fall within the experimental region. So in general, it may not be a big deal as long as you're not extrapolating, but if possible, we still would prefer not to have multicollinearity occurring. So software checks for multicollinearity by computing R-square values for regression in which the dependent variable is taken to be one of the k x's and the predictors are the remaining x's. So for example, when k equals 3, there are 3 relevant regressions that we could look at. And so those are those 3 different ones that we could look at. So each regression yields an R-squared value, and in general there are k such regressions and therefore k resulting R-squared values. So if any of those R-squared values are close to 1, you generally are going to have multicollinearity. And so SAS will compute what is called a variance inflation factor, which is a function of those R-squared values. And we've actually seen variance inflation values in the SAS output before, we just haven't talked about it. So a VIF of 5 indicates moderate multicollinearity, and a VIF of 10 indicates severe multicollinearity. This is just a standard. I actually pulled this from the Mendenhall book, so you will notice that some texts and other resources might use something slightly different. There are several remedies, and again, I'll let you read these on your own. But let's look at an example here. So consider the following data set. We're going to use age and years of experience as independent variables to predict salary. So notice based on the following scatter plots, we see there's a positive linear association between age and salary and between years of experience and salary. Also, if we think about age and years experience, those things are probably correlated with one another. People that are older tend to have more years experience in their job. Now that doesn't mean that that is going to hold for everyone. And it could be that actually in the current job market, this might even be changing as people tend to not stay at the same jobs for as long as they used to. But it definitely used to be the case that the older you were, you tended to have more years of experience. All right, so we have this multiple regression model. Notice here we're just looking at the model that has the two main effects. And here is the SAS output for that model. So notice here, we have the variance inflation factor for years and age. Since we only have two predictor variables, the VIF will be the same for each of these. So looking at this, we can see that that variance inflation factor is very high, suggesting the presence of multicollinearity, which again, thinking about what our two predictor variables are, it's not surprising that we see that we have high VIF here. And so in this case, we may want to consider only using one of those predictor variables in our model. One other pitfall we have mentioned before when we looked at simple linear regression is the idea of extrapolation. So for simple linear regression, we discussed how we only want to make predictions or estimates that pertain to y for values of x that are within the range of the experimentation. Predicting outside that range is extrapolation and less reliable results that we have stated. So for example, if we look at what we have here, for this example, what we're saying is our observed x values only fall in this range. So when we fit the model based on our data, this is our fitted regression line. Past where we have observed data, in other words in this range, we have no data to inform us what is happening. So we have no idea if this line keeps on going straight or if it verges up or verges down. So we always want to be very careful not to extrapolate, and we really just want to rely on our observed data to predict what is happening. Now in the future, if you learn about time series, you'll see that that is a little bit of a different case because in time series we often have to extrapolate. Now, in multiple regression, it's a bit more challenging to establish the range of experimentation. So here's an example. Consider two independent variables, x1 and x2, and here are our observed variables. If we look at the values for x1, notice the minimum for x1 is 1, and that the maximum for x1 is 3. So in other words, if we drew in our range for x1, we would see that x1 existed between here and here. And then if we looked at x2, we would see that the minimum for x2 is 10 and that the maximum for x2 is 13. So in other words, looking at x2, here is our range. So if we weren't careful, we may think that we would be fine predicting anywhere within the yellow box. But if we actually look at those individual data points, we can see that really we just have data within this shaded shape, not the entire yellow box. So we want to be very careful because this is what's known as hidden extrapolation. So if I try to predict, let's say, at this point right here, I would actually be performing hidden extrapolation because I don't have any data for my predictor variables within that region to help me estimate what's happening there. And this is going to conclude this note set.